All right, we're going to look at Mechanics 3 from 2006 just from another perspective. We're going to look at the energy version. And so when we do the energy in 1D motion problem, we're actually going to end up solving for part B first, then part A. All right, so the setup is the same. We do have to kind of include now, though, the height that is initially at. Now that height it is initially at over here, which I just called h, that height is equal to the hypotenuse L times the sine of the angle. So it's still going to be in terms of the variables we need it in terms of. Because it's both rotating and moving when it reaches the bottom of the incline, and I mean the ring, it's going to have a kinetic energy that's rotational and a translational kinetic energy component. And because it's rolling without slipping, we do have a relationship between how fast it's moving, the center of mass velocity, and how fast it's rotating, the angular velocity. And we also do have this relationship between alpha and A. Now, we're going to set up that equation for the work kinetic energy theorem that we expanded. We're going to cross out work in because no one's applying a force. There's no kinetic energy at the start. The height at the bottom is 0, and there's no springs. Now, we just did the problem with forces, and yes, there was a force of friction, so obviously there's going to be some work done by friction. Now, the problem we run into here is there's actually not any work done by friction because it's not actually sliding. What that force of friction is doing for us is it's taking and it's adding some of that energy into rotation. Okay? It's making it roll. It's not actually slowing it down in a sense that it's taking energy out. So we really don't have any work done by friction here. So our equation then becomes, and we can just move this UG1 to the other side, is I get UG1 equals K2. And so we start to solve this. Okay, so I have MGH equals K2. Now remember, it's going to have both 1/2 mv squared, but it's also going to have that 1/2 I omega squared, where our I value is mr squared, because we're dealing with a ring. And we will also make a substitution for, of course I'm not moving enough, huh? We'll also make a substitution for omega, and it is going to be V over R. So I have V squared divided by R squared here. Now the nice thing about doing that, my R squareds cancel. Okay. I also have an M in every term, so we can get rid of that. I have 1/2s over here, so I can get rid of those and just make this 2GH. Okay. And so what I'm left with is I'm left with V squared plus V squared, so I'm left with 2V squared equals 2GH. I guess I could have left the 1/2s because they're going to cancel out here. And so I end up with the speed is equal to the square root of GH. But remember, we said H was L sine of theta, so I'm actually left with V is equal to the square root of GL sine theta. And there we have part B. Now we're going to go ahead and take part B and use it to find part A. So we'll move the camera here. Good. Stationary. All right, we're good. So we have a constant acceleration problem. Okay, so we just found the speed at the bottom of the incline, and it was the square root of GL sine of theta. And we want to find the acceleration. We don't really care about time, so we'll pick an equation without time. That will be equation number 1. So we have V squared equals V naught squared plus 2A times X minus X naught. Okay, and X is going to be L, the distance it's gone down the ramp. Starts at rest, so V is 0. Okay, let's cross anything out that's 0. And now we're just going to solve for A. So I'm going to have V squared divided by 2X equals A. We'll make some substitutions. So I end up with GL sine theta, square root squared, so it's just that, divided by 2 times the length, L. The L's cancel, and my acceleration I'm left with is G sine theta over 2. And so here is your answer for part A. So we did part B first, then part A with this method.